Hello everyone, my name is Mustafa Alperen and this is Lab 4 for Physics 2212, bar magnets. So a quick table of contents of what I'll be covering this video. I'll have an introduction, I'll go over the initial variables, the details of the experiment, as well as the overall data sheet we got. I'll go over my coding, the results, and what if or what does it mean. So the purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet. To do this, we use three main laws. The Biot-Savart law, which relates the magnetic field to a current element and is expressed as mu0 over 4 pi q v cross r over r squared. The magnetic field of a dipole, which is that a magnetic dipole is similar to an electric dipole, but just has closed circulation, represented as mu0 over 4 pi cubed 3m dot r time minus m, as well as the distance-dependent formula, which is the magnitude of a bar magnet's magnetic field decreases with distance. B equals k over r cubed, where k is just a constant. And a main preview of our results is just that n was minus 2.2943 and the magnetic dipole moment was 5.98. So if we go to the initial variables, our models was just the natural log of bx time by a natural log of r graph, which you'll see later. I have that. We assumed that there's no magnetic field affecting the magnetometer other than the magnet and the Earth's magnetic field, and the Earth's magnetic field should be technically as minimal as possible since we aligned it. The system and the surroundings, our system was the magnetometer, the surroundings were the bar magnet and the Earth, and anything else that's just sort of interfering and is there. The initial conditions we had was just that the magnetometer's axis set is equal to 0. So to just set this up again, we line our phone up with the magnetic north using the magnetometer app, align the meter stick, put the bar magnet at the end of the meter stick, and then move the phone up and down the z-axis, find where the y component's a minimum, rotate the phone to put a tape there, find where the x component's minimum, put a tape there, and where they intersect is where the phone's magnetometer is. So by doing this, we get sort of this data sheet. You can see on the right is the ln of bx by ln of r sort of graph, and you can see that the left side and the bottom side is where the data is. Okay. So here's our code. In the middle section is where we start, where the top of the code is. And we didn't change much here. The only thing we changed was that we put the magnetic field of a dipole, which we calculated as 5.98 over there, and then we calculated R mag by using square root of Rx squared plus Ry squared plus Rz squared, and then did R hat by R over R mag, and then used the Biot-Savart law to calculate the magnetic field there. And then to get the 6 points, we did distance 0, 0, minus distance 0, 0, 0, distance 0, etc., all in the XYZ, all positive, negative. That gives us 6. And then we went along with calculating the thing for each place, as well as putting the arrow on each place. That's what's down there. And then through calculating this, you can get a dperp of 0.19167. That's over there on the left-hand side, which is after the right-hand side. But the results, there was like some similarities between our data, but it wasn't also too similar, so there were some things causing an error in the lab. And here in the bottom two photos, you can see the part on the left, the b-axis 1, b-axis 2, perp 1, perp 2, etc. That's the results we got from our coding, and these yellow boxes are the results we got from the uh, data in real life. So there is some possible sources of error here, which is making them differ by something. And some error might just be that we've not set the magnetometer as close to a 0 as possible, so there's some sort of interference from Earth's gravity. Or there's just measurement errors. We didn't get the x as close to 0 or as y as close to 0 as we could. Or there's just some other objects, maybe like other magnets interfering with the magnetic field. And what if, or what does it mean? What if we hadn't oriented our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? What would have changed? The Earth's magnetic field in this case would have interfered with our lab, causing errors which cause like a deviation from what the normal lab results would have needed to look like. And what if we were to stick to identical magnets end to end and run the experiment again? What would change in our experiment, if anything? So since the positive end and the negative end of the magnets would still be in the same direction, the only thing which would be changing is the magnitude of the thing, and that would change by 2 times since there's 2 magnets, and accordingly all other measurements would also increase by 2 times. And thank you all for listening. Yeah.